Hello everyone, welcome to the AI track of the Open Day. Our next speaker is Stefan Bergstein, Senior Solution Architect at Red Hat. He will speak about AI and ML in the industrial edge with Red Hat OpenShift. With a combination of edge computing and AI and ML, bringing processing power closer to data can help to productively discover potential errors, improve product quality, and reduce potential downtime. In this talk, he will explore a manufacturing use case that needs to capture senior information from line servers and route it to the one-site factory cluster, where data can be analyzed in the real time with AI and ML models. This data can then be sent to the centralized data center or cloud for further processing and storage. He will cover how within this use case that is done in a single plant location can scale to multiple sites with consistency to meet the needs of modern manufacturing organizations. So, Stefan, the floor is yours.
Welcome to the talk Machine Learning at the Industrial Edge with Red Hat OpenShift. In the next 20 to 25 minutes, I will walk you through a use case and an architecture that we developed with clients in the manufacturing industry. But before we dive into technical details, the machine learning lifecycle use case and the demo, let's first have a quick look at the manufacturing industry itself for this use case. So what is the manufacturing industry? This is actually now here a rather opinionated view because of our internal structure. But we as a team cover mainly three big areas. So the industry we see really as a provider of goods that are produced in their plants, and therefore also the relationship to edge computing. And there are various things that are produced. For example, high value assets in the automotive industry, or shipbuilding, trains, aerospace and defense, but also consumer goods and industry parts. So consumer goods, electronics, home appliance, power tools. And last not least, with this edge use case, we are also addressing the process industry. That means mainly, one hand, chemical companies or pharmaceutical companies, which also have the need for next generation edge computing. What we see here is an illustration of various edge tiers. So on one hand, in the middle here, the enterprise core or the provider tier, then the provider edge in the middle, and on the far left, the end user premises edge. The data center core, that's what we all know, what companies have in their data centers or their applications running, either modern application, web application, traditional applications. And on the far left, here we talk about, in this context, about the plants. And the middle tier, the provider edge, is mainly offered or provided by telecommunication provider to get the communication from the core to the end user premise aligned and operable. Let's have a little bit closer look at the edge here, because with the factory edge, we have here the use case of running applications like manufacturing execution systems, also having use cases like predictive maintenance. And one challenge is here the different stakeholders and the different technology. So you have on one hand the OT, the operation technologies, these things like PLCs or human machine interfaces, SCADA systems that really running the plants. And then already today there's a lot of IT, these rack mounted systems, maybe a small server room or really a small data center when it's a big manufacturing plant, providing the needed IT technology. And what's also specific here, that there are requirements, especially around firewalling and closed systems, because yeah, there's a high need to protect manufacturing plants from any kind of attack from the outside. Talking to clients in the manufacturing industry, we have a couple of themes that are coming up over and over again. Especially, yeah, we have a focus on modern software development life cycles and rolling out software and doing also machine learning in a new way. For example, using also a container and Kubernetes for deploying machine learning models. But what are the themes here? And on one hand, it's all about capturing a lot of sensor data that can then be stored in a big data approach. Because here's the goal to use the data and analyze the data for uses like optimization and planning of the production, but also about traceability and analytics on the shop floor. When talking to large customers which have a lot of manufacturing plants, there's also the concern or the question to optimize the various configurations of the OT and IT technology. So think about large customers with hundreds of manufacturing plants. Even when in the plants, the software that's running is kind of standardized, but there are different kind of versions and they need different kind of settings. And a question what we discussed is also how to optimize the rollout of this kind of configuration. And yeah, the software development and release cycle. So the question around how to speed that up, because traditionally you have maintenance windows, software rollouts only maybe every quarter, and we know from the from the data center, from web applications, that we can update software every hour with the right CI/CD approach. And the question that we discussed early on with the customer was all about how can I do also CI/CD, not only the data center, but also from the data center into the manufacturing plants. The use case and the scenario for doing AI and ML for the industrial edge with Red Hat OpenShift has around 6 major use cases. The first one is around data engineering and machine learning model development. What we have here is an integrated development environment where data scientists and data engineers can work and can also share data and can also share expensive resources like GPUs. The second area is around how to build and test intelligent cloud native applications. So cloud native because clients want now develop and deploy container-based applications, and intelligent because these applications use machine learning models to make certain kind of decisions. And what is needed here and what we offer is a container-based continuous integration and continuous deployment approach with pipelines. The third area, and that was also in the center with the discussion with the clients, is the declarative configuration management. Not only for the application in the core data center, but also in the edge, because applications span that various areas. That means an application has parts in the data center, maybe regional data center, in the server room of the plant and at the production line. What we developed here and applied here is a distributed GitHubs approach for industrial edge. The fourth area is more classical here around machine learning, serving and monitoring. The need also to deploy machine learning models in containers and doing also the proper monitoring to capture the model performance, eventually also detecting some model drifts. And the fifth area is the actual application. So here, a typical application for that engagement, what we used here is a condition monitoring application. What we have in the demo is kind of a demonstrator, but customers use either their own condition monitoring or a packaged application, which is now then enhanced with machine learning functions. And last not least, the area of capturing the edge data into either first and also locally in the plants, but also then getting the data in real time into a central data lake on one hand for certain kind of analytics functions, but also then to use that data to retrain the machine learning models. Let's come back to the first topic of the graph that we've seen in the previous slide. It's all around an integrated machine learning development environment. What we offer here as a project on top of Red Hat OpenShift Kubernetes is the so-called Open Data Hub. And this Open Data Hub gives machine learning and engineers or data scientists the tools and the environment to work on data and to develop machine learning models. What they usually would get is then access to Jupyter Hub spawner so that they can select a notebook image, or then eventually the need for GPUs, and then later on, once it's started, it gets the typical Jupyter Lab environment. Let's try to switch now to a different kind of view. This is here the console, an OpenShift console, and I would like to give a brief overview of the operator that provides the Open Data Hub. If we jump into here in the installed operators and just briefly open the Open Data Hub operator, you can see the description and also the various components that this kind of operator provides on Red Hat OpenShift. Yeah, and when a data scientist gets environment, yeah, it's something typical like what you see here with the Jupyter Lab. And you see also that the notebook here that we have it for this demonstrator, because we're doing condition monitoring, and that's a really simple model for detecting anomalies for temperature and vibration data. Once the machine learning model is developed and then tested and validated with reasonable quality, we would like to deploy the model to the manufacturing edge. And what we do in this approach, in this solution, is we're using the same pipeline. That means we're using here the Tecton pipeline. Tecton is the upstream project, and in OpenShift, the feature is called OpenShift pipelines. We use the same pipeline approach here for application components. That means for a dashboard and for various components that belong to this application, but also for the machine learning model. And what we do is actually we grab the model and we build a container, a certain core container that has then the model built in. So that means the whole idea of then building the container like in this pipeline, and then putting it into a container registry so that then the container can be deployed to the right site. I mean, the right manufacturing site. And where what we see here as a screenshot is the small pipeline. Only to highlight a few steps, we are cloning the source code. We're also cloning a GitOps repository. I will come to GitOps in a minute. We build the container with the source to image build, push push the new version, and instructing also the GitHubs engine to deploy this in the test environment. And when the tests are all good, we are then triggering the rollout into production. And yeah, here again, the OpenShift console with the pipelines that would was looking like this. We can look at previous pipeline runs. That is here, yeah, the same where I had the screenshot before. That's the build of and test of the IoT anomaly detection. And you see now all steps in green because the whole flow of building the container with a new model and incrementing the versions was always successful. Now we come to the use case of declarative configuration management with a distributed GitOps approach. Yeah, just to come on the same page, the GitOps principles, and I think the idea of using continuous integration pipelines for software development and software integration and software release is well known. Here on the picture on the right, you see the flow where the developer is going ahead and checks in code, changes code, and the CI pipeline is running, and the an outcome is here a new container that it's then stored with a certain tag in the container repository. Putting then also GitOps in perspective, using then GitOps workflows and principles also for the deployment. And that means having a repository that describes a deployment, like what kind of containers are used, what are the YAML files for Kubernetes applications, and having that all checked in Git. And with the same workflow like for code, that you roll out new releases because you're accepting pull requests, you're then instructing an GitOps controller. And in this case, we have here Argo CD that reads then all the definition of the manifests, so all manifests, and then enforces that on a Kubernetes. And in this case here, enforcing then the configuration settings on a Red Hat OpenShift Kubernetes, and in a distributed way. It's not seen on that slide, but in a way that this kind of enforcement is done on the in the central data center, but also in the factory data center, so that you're coming then to a completely consistent approach across the sites. I like to show you the GitOps approach in context of the configuration management use case. And what we see here is the UI of the condition monitoring demonstrator. And what we will now do, we will inject via Git and configuration change. And for simplicity, we don't do this with the whole pull request workflow, but we can go now here in the repository that represents the configuration, and we have here, for example, for sensors, configuration properties. And when we are going now here into this one and edit this configuration and set a certain kind of settings, like here the temperature settings, enabling the temperature sensor, setting then this to true, and just commit the change. Again, not with the full life cycle of pull request. We can see now here in this Argo CD, that means the GitOps controller, when we sync these settings, that means when we're synchronizing this again, because this is pull based, then we see that new configuration gets pulled in, and also that here, for example, the machine sensor is getting this new configuration. We sync should have happened already, or can I do this? I will trigger that already again manually. So that means it gets the configuration from Git now and redeploys it. That means here you see the pods and the various settings here, like config maps. And now more or less automatically, not more or less, really automatically, you see that sensor 2 gets a new configuration. And once that is completely deployed, we can also look at the dashboard, because now the dashboard will have also an additional metric which is already coming in. It means through this config approach with GitOps, we're getting now new data into the system. Now we are at the model serving and model monitoring part. On that diagram, you see a simplified version of the overall architecture. I won't go through each and every step here, but for the model serving, I wanted to highlight here in the middle the applications running in the factory, which gets MQTT messages from sensors, and one part of the application is then invoking the REST web services for anomaly detection. And this is the anomaly detection web service run containers built with Selden Core. And beforehand we discussed the whole process of doing CI/CD and image building, also for machine learning models. And the monitoring part, most likely you're aware that Selden Core has really a lot of benefits, and one of them is the metric part. And here, very small, you see illustrated the dashboard. But what we also can do, we can jump over to the dashboard here, which you see directly now in full screen, hopefully. And you see then the typical data here, like on one hand, the sensor data with the predictions here, but then also the metrics of the Selden Core API dashboard, like how many requests per second is coming in, and the latency, something that you would be interesting to observe the model then in production. On this diagram, again, I would like to walk you through the use case of capturing the data in the manufacturing plants, and then also bringing them into the central data center and storing them in the data lake. For example, a typical flow here is data is coming in and captured through MQTT, inserted. The first step for the data flow is that it's going from MQTT via CamelK route into a Kafka, and to have also the data captured here at in the factory data center. At the second step, we are using Kafka Mirror Maker. It's to get the data from the factory to the core data center. And the beauty here of using Kafka Mirror Maker is that we can then configure the direction of the communication, because mentioned before that these environments are highly firewalled and restricted, and with Kafka Mirror Maker we can control which component is opening the connection, and so that we don't need to have any kind of inbound connection into the factory. And then the data flow is then going along with having the data then in Kafka in the central data center, and again with a camera route we aggregate the data, and not aggregating but putting them into batches, and then storing them into a data lake, which is based on OpenShift container storage, which then gives later on the data scientist access via standardized S3 protocol to take the data and to, for example, for retraining the models. I like to sum it up with a view on Open Data Hub. This picture shows the various components and the platform where the component is running. And yeah, you see here the components that we had a look in this use case and that we used for the use case. For example, the storage components or the data in motion components like Kafka, and having Ceph-based data storage that we used, but also components and functionality for data scientists, having on Red Hat OpenShift running, or Jupyter Hub, Selden in the factory, but also in the data center. And there are also various components that we haven't used in that scenario. All this is running on Red Hat OpenShift Kubernetes to bring the right stability and scalability for the system. At the side, you see also additional products that are useful in that context, like single sign-on services, like API gateways that you might want to use, but also then monitoring orchestration services. Yeah, and we had a look at the Grafana dashboards and data that we saw were obviously collected through Prometheus. And the pipelines, either Jenkins pipelines or Tecton pipelines, that we use for building the software components, but also then the components that have the machine learning included.